everybody, this is Ms. McBride and we're going to be covering section 4.2 here. This will be one of the shorter, easier sections, so you'll be happy to hear that. We'll be talking about shapes of distributions. So you're going to be able to describe the general shape of a distribution in terms of its number of modes. We'll have vocabulary for that. Skewness, vocabulary for that. And variation we're going to talk about for about 1 second because 4.3 is all about the measures of variation. We're going to take a look at a distribution. So remember, a distribution is just all the data that you've gathered. If you put it into a histogram and then you connect those top points like we did before, now we're going to take a look at describing what we're seeing. So we're looking at the general shape. So we kind of do like, just connect the dots along the top to get that basic shape going here. So the smooth red curve there approximates the shapes of the distribution. So you can see they're very different. So we need some words to describe what's going on here. So the number of modes, remember that's the most frequent, is the first thing we'll take a look at. We have a uniform distribution if all the data values are pretty much the same across. It has no mode, no high, no low, it's just the same frequency. An example of this is if you'd be rolling die 100 times, you would have pretty much roughly equal the same amount of times you rolled a 1 as a 2 as a 3 as a 4 as a 5 as a 6. So if you made a histogram of the number of times you got a 1 through a 6 when you rolled the die 100 times, you get pretty much a uniform frequency across the top. The other ones we'll see lots of examples of here. So if we have a single peak, it's called a unimodal distribution. If I have more than one peak, 2 peaks, it's called bimodal. And again, here the note says any peak in a distribution is considered a mode, even if they're not all the same height. So that's okay. So in the diagram C, you have 2 modes because you have 2 like humps. In the third one, we have 3 humps, otherwise known as trimodal. So one mode is unimodal, no mode straight across is uniform, and then I can have bimodal and trimodal. After that, we don't give it a name. Now the second thing we want to look at is the symmetry and the skewness. So remember, your definition of symmetric means if I put an arbitrary line through the middle, it's going to be a mirror image across that. So if you fold it across a center line and you get a mirror image, it's called symmetric. So these lines of symmetry here are an example of each of these types. They're all symmetric because if I folded one across the other, across that line, the left half would pretty much match the right half. It doesn't have to be perfect, but it has to be roughly the same. So we still have our single peak unimodal, and then we have our trimodal as the third one, and that middle one is still a unimodal. Still got 1 peak, it just doesn't have exactly the same shape. All right, now when we're talking about our distribution and it's not symmetric, we need some more vocabulary. It tends to be spread out more on one side than the other. We say the distribution is skewed in that case. All right, so now figuring out how to name these, the way I always talk about it is, notice you've got one piece that's pulled way out. That's called the tail. So for your left skewed, you have a tail that's out to the left. So it's like if you took a hold of that left end and pulled on it outward, it skews the tail. So the tail is left skewed. It pulls the tail there, or the tail pulls the skew. All right, so when you've got your right skewed, just imagine it had started out symmetric, and you grabbed the right end and you pulled it out to the right. So that's your right skewed, and your symmetric again is basically centered, and notice that the mode equals the mean equals the median. That's going to be important when we get to the chapter on normal distribution. So if it's nicely symmetric, your highest point is the same as your mean, is the same as your middle point. That's symmetric. Now let's go back to the right skewed. Notice it says the outliers are the high values there in blue. that means you've got some outlier out there that's pulling the mean out that way. That's important because when you go to look at what is the best average to use or the best measure of central tendency, if you've got a skewed graph, your mean is not your best choice. Notice your mode has most of the data values because that's your high point. The mean is to the right on a right skewed graph. Now look at your left skewed. The mode again is the best way to look at it because it's got most of the data values there, and the mean is to the left side because there's an outlier over to the left. So if you have an outlier out to the left, that means your mean is going to be pulled or skewed over to the left, and you're going to have a left tail. That right skewed, your mean has been pulled to the right because you have an outlier, one value that's way high out to the right that pulls the skew that way. And symmetric, your mean is right in the middle. It's the same as the median. So in that case, the mean is your best measure of central tendency or average. So again, skewed to the left, the mean and the median are less than the mode. If it's skewed to the right, the mean and the median are greater than the mode. And for a symmetric, they're all the same. And this is going to be important in choosing some ways to look at things shortly. So which is better measure of average or the center for a skewed distribution? All right, I talked about that already. It's going to be the median because the mean is being pulled towards the tail there because of some outlier. So the best measure then would be the median, which would be the better way to go because it hasn't been pulled by that outlier. All right, so let's look at a few examples. All right, now if I was in class, I'd be drawing these pictures on the board, but there's no good way to draw on this PowerPoint, so I just have to visually discuss it. All right, so each of the following situations, would you expect it? Now remember, expect means typically happen. Don't come up with a, well, what ifs or whatever, it's just expect to happen. So the distribution, is it going to be symmetric, left or right skewed? So if we have the heights of a sample of 100 women, so if I just had 100 random women from a sample, line up, take their heights, and draw a histogram of it, you're pretty much going to have that unimodal bell-shaped curve. Therefore, it will be symmetric because you'll have roughly equal numbers of women who are shorter than taller than the mean, and the extreme heights are rare on either side. So you have no extreme on either end pulling the tail out. Now the family income in the United States, that'll be different. Most people make around $50,000 or so according to the statistics here, but you've got some people who make, very few people who make a whole lot more, so that's going to pull the tail out to the right. Now the speed of cars on a road where visible patrol cars using radar, now my husband does this, I don't know about y'all, but he hits the brake. I'm like, are you crazy? They're going to see you hit the brakes. So all of a sudden you've got people who are going slower than you expect them to because of that patrol car. So that's going to have some unusually low numbers. So that's going to pull your mean a little bit over to the left. So that would probably be left skewed. So again, same idea here. Those few high income families are going to pull that mean to the high side or to the right. And the drivers that go really slow because of the speeding guy are going to give you a few unusually low mean values, which is going to pull your mean to the left skew it. Now I like how they just throw in this speed kills, so be careful. So does texting and all that. Or actually distracted drivers, they're finding out any distraction is bad, whether it's texting, even talking hands-free. One of the worst accidents ever back in San Francisco when we used to live out that way was before cell phones. It was a lady trying to get the radio station that she wanted, and she took her eyes off the road and slammed into somebody in front of her and caused a huge multi-car, multi-death accident on the Golden Gate Bridge. So keep your eyes on the road is the idea there, and slow down. All right. So in ordinary English, the term skewed is often used to mean something that is distorted or depicted in an unfair way. So in terms of statistics, skewness then would mean it's a distorted symmetric graph. So your normal curve we'll be learning about is when the mean equals the median equals the mode. That's symmetric. If you distort it, you skew it by pulling it either right with a tail or left with a tail, and that will be because you've got some outliers pulling that mean left. All right, measures of variation. We're just going to do a quick definition here. It just describes how widely the data is spread about the center of the data set. And we're going to discuss a whole lot of this in section 4.3 on the different measures of variation. But for now, let's just take a look at how the data is clumped. That's how I think of variation. So low variation, notice it's all clumped way around that center value. These are all unimodal, so my mode is very high, and my data values are all clumped really closely to it. I say here I have a low variation. Moderate, it's kind of spread out a little bit more. High variation, you've got the data is spread, so it's like you pull both ends and pull in both directions. And notice as the ends get pulled out, the center gets lower. In the moderate one, as the end gets pulled out, it's a little bit lower. And in the low variation, I'm really very high in the middle. So the amount of area we'll learn under that curve has to stay constant. So if you start with it clumped way in the middle and you pull it from both ends outward, it's going to cause that distribution to spread out on the ends but get lower in the middle. All right, so that's variation. It's how widely the data are spread about the center of the data set. So how would you expect the variation to differ between times in the Olympic marathon and times in the New York City marathon? Well, the Olympic only has those elite runners, so it's going to be very tightly clustered. You know how they all come in really close to each other. The New York City marathon, on the other hand, allows for runners from all abilities, so this variation is going to be much greater, spread out about the center. All right, let's look at some textbook examples. So I'm on page 134. So here we have, I did the word example next to the picture, so work sideways here. So Old Faithful has the picture that goes with it to its right. So the histogram here shows the time between eruptions of the Old Faithful geyser. Over the histogram, if you were going to visually draw a smooth curve that captures the general features, then classify it according to the number of modes. Now let's do that first so we can see it's bimodal, has two humps, if you will. Its symmetry or skewness, and this is not symmetrical. And you really can't even say it's skewed because it's not really pulled to the left or to the right. Now I will mention that your book says that this is left skewed. To me, that's kind of pushing that just a little bit because you don't really have a tail, but there is less over to the left, so you could kind of make a case for it. But generally, I would say that was bimodal, a really slight left skew, and a wide variation because this is, the data is spread out a lot more than the center would be. All right, chip failures. This is a classic picture here. So remember, we always want to take a look at what's happening here. So here I have failure times of computer chips. So I have a whole lot that are failing between 0 and 2 months, and then a whole lot less that are failing the farther out you go. In other words, not that many last out till 10 months, over 108 computer chips. So if we draw our smooth curve, this one is a beautiful right skew. So you see how it pulls the tail out to the right. It has number of modes. It's just one. I got one high mode, right skewed, and a moderate variation. It's not really spread all over the place, but it's not really tightly clumped either. All right, so that's number 10. Number 11, we've got our rugby weights. These are the weights of rugby players. Well, even though they all may be a little bit heavier than the normal population, because I got all rugby players, I'm going to get this nice symmetric curve here. And this weight's in kilograms, so somewhere around the, between 90 to 100, 110 in there. So it's a unimodal. It is perfectly symmetric, and it has no skewness. So single-peaked unimodal, almost perfectly symmetric, and a moderate variation. It's not super tightly clumped, so it's kind of spread moderately, not way spread out, not tightly clustered. All right, now let's look at the baseball salaries, number 13. So in a recent year, 817 professional baseball players had salaries with the following characteristics. All right, so there's the mean. Oh my goodness, 3,250,000 and change. Now the median, notice, was 1,152,000. So if I'm plotting this on a scale, so if you get a piece of paper out and do your number line, the median is going to be my middle. My mean is to the right of that. I immediately know this thing is going to be pulling over to the right. It's going to be right skewed. But most of the salaries range from a low of 400,000, whoa, to a high of 33 million. Look at that. So describe the shape of my distribution here. So it's definitely going to be right skewed. Those few super high salaries really pull the mean over to the right. All right, it's not going to be symmetric because we can see that the median is not the same as the mean. So that immediately tells me it's not symmetric. It's going to be right skewed. And let's see, part B, about how many players had salaries of 1,152,000 or higher. All right, because it's about half of 817, it'd be about 409. Now I know it's half because it's the median. All right, so if they tell me my median, I know that's my middle number, so half are above and half are below. Since there was 817 professional players, half of that is about 409. All right, let's take a look at describing the distributions, and then we'll be finishing this up. All right, so here the directions say, answer the following questions. How many modes, again, would you expect? Would you expect symmetric left or right? All right, so for number 15, the annual incomes of those in a statistics class, including the instructor. Now this one I chuckled, and I chose it on purpose because they are assuming what I call a typical 4-year university dorm live-in kind of situation. In those situations, the students really aren't making any money or have a really small part-time job, and the instructor's the one who's the highest paid comparatively. Now, we're at a community college. I work at a community college, and I have a lot of students who are working full-time. I have a lot of students who make more money than I do, depending on why they're coming back. Some of the nurses who are coming back to get their BSNs or go for masters. So if we answer this question in the expectation of a 4-year college where we have all the really young students who aren't working, then the teacher would pull the mean out to the right because they would have a much higher salary and most of the students are making zero or very low income. So that would be a totally different answer depending on which college you look at. So the typical college would be a single mode of about $0. So how many modes would I expect? 1. And then it would be right skewed because most of the students are making little or nothing. Again, that's at a 4-year school. If it's not, I wouldn't even say it had a mode at all. Wouldn't know for sure. So we'll just go with the expectation of a 4-year dorm college where most of the students are full-time students. All right, number 18. Now this one, the heights of 500 male students, this is going to be much more expected type of thing. Half of whom are adults, and the other half are only 8 years of age. So envision this. You've got your adults who are going to be up on the tall, obviously, end compared to the 8-year-olds. So I'm going to have a bimodal here. I'm going to have 2 modes. but it's still going to be roughly symmetric because you're going to have as many, if half of them, so what, 250 adults and 258 years old, you're still going to have pretty much a symmetric graph because you're going to have just as many in the center of each, etc. So imagine two perfectly symmetrical humps. All right, now the last one, patients. Here we have the ages of 1,000 randomly selected patients being treated for dementia. Well, then you need to know that most dementia patients are older. So the ages then are going to be higher. So you're going to have a unimodal with your big lump over on the right-hand side. Sorry, did I say left? Should be right-hand side for that one. Yeah, sorry. I'm trying to envision it in my head as I'm thinking. So those being treated for dementia, most of them are going to be lumped on the high end, and your unusual ones are going to be your younger ones. So this will have a left skew. So make an vision of that. You've got just a few people in their earlier years who have dementia, and then most of them are going to be up in the 60, 70, 80-year-old range. So you'll have a one mode, unimodal, but it's going to be skewed to the left because those are going to be the unusual values. All right, that's pretty much 4.2. Go ahead and fill in your notes. Hopefully you're doing that as you went. Make sure you get those submitted. I'm having quite a few people not submitting those notes. And go do your homework. All right, thanks. Bye.